Okay, we are ready for the next talk by Ben Keller. He will tell us about entropy-driven winds and superbubbles.
All right, can everyone in the back hear me well? Okay, wonderful. I'd first like to start out by thanking everyone at the SOC in particular for bringing me up. This has been a wonderful conference so far. Great food, great conversations. I'm a Humboldt Fellow now at the University of Heidelberg, but I'm going to be talking mostly today about a mixture of things I did during my PhD at McMaster University and a new project that I'm working on now. And to just start us out and ground us with a little bit of motivation, let's talk about the Milky Way. So the Milky Way is a typical L-star galaxy, which means that it has a stellar mass to halo mass fraction of a few percent and a very small bulge. So if we go back to the state of the art for simulating galaxies like this, around 2012, we find that the average simulator was having a lot of problems actually getting the realistic properties that we see in the Milky Way. So whether you're looking at one different code or another, one set of feedback physics or another, nearly everyone was producing too many stars, and nearly everyone was producing these stars in the bulge. So this is sort of the problem that I sought to tackle during my PhD. And since then, things have more or less improved. And they've primarily improved by looking at the physics of feedback, changing either what we include as part of our feedback, including things like stellar winds, radiation pressure, even exotic things like cosmic rays, or changing the way we implement this physics numerically, either by putting it in as a non-thermal form of energy, perhaps some sort of unresolved turbulence that doesn't cool away, by adding it as kinetic energy, or even by disabling cooling. I decided to take an approach that looked not at how to deal with this from a numerical standpoint, but more at the sort of first principles physics and what's going on. So we know that quite often, massive stars can form in massive clusters. And the kind of clusters that we think are important for driving a lot of the outflows in galactic winds from galaxies that are in starburst modes or galaxies at high redshift typically include hundreds or more individual massive stars. And as we heard today from many different speakers, these supernovae can overlap to form a superbubble, and these superbubbles couple to the ISM much more efficiently than an equivalent number of isolated supernovae would have done. There's a bunch of really excellent work by a bunch of people here in this room today that have shown exactly that. And so we developed, during my PhD, a 3-simple-piece model for capturing the effects of superbubbles in cosmological galaxy simulations. And the key component that all of these pieces rely on is thermal conduction and mixing. So we know that thermal conduction can act as a heat flux, but it also can act as a mass flux in the opposite direction. This mass flux, as Martin talked about earlier today, is very important for mixing what the shell material into the hot interior. And whether it's driven by conduction or turbulence is still, I think, not an exactly closed question, but at the very bare minimum, conduction should be driving a mixing process. This is a process that's been absent from previous models. And because this evaporation, this mass flux, has been missing, up until now, other models of feedback couple an amount of mass from the ISM that is really set as an arbitrary numerical parameter. So by including a model for superbubbles, where a shocked thin ISM shell is mixed in with this hot bubble through thermal evaporation, we can actually get a physical measure as to how much material is actually heated. And the 3 pieces that we use to implement this as a subgrid physics is 2-phase particles at the earliest stages, a stochastic evaporation model for once that bubble becomes large enough to be resolved, and thermal conduction to mix heat within the bubble. So the first thing we did was actually validate this using high-resolution, isolated superbubble models. You can see the beautiful Vishniac instabilities, like in the the simulations that Martin showed earlier today. And we found that this matches quite well with some analytic studies that were done earlier by Sillich et al. We then used this to simulate a set of isolated Milky Way-like galaxies. And an important feature of what we found is that with this new model that correctly couples the right amount of mass to your feedback energy from supernova, you get a phase diagram that makes sense from a physically intuitive standpoint. You have a warm ionized medium that cools to form stars, and those stars detonate as feedback, as supernova, giving you very hot diffuse gas that cools along an adiabatic. So if you take a look here, you can see this line here is a line of constant entropy, and you can actually track in cosmological galaxies, as this outflow gets further and further away from the galaxy, you're getting lower and lower temperature, but keeping the same entropy. So in other words, you pushed yourself into a regime where your cooling times are long. Our next step with this was to turn towards cosmological galaxies. And we decided that what we were going to do was re-simulate a sample of 18 L-star galaxies that had been previously simulated in 2010 using an older method for the hydrodynamics, as well as a blast wave feedback model that used a cooling shutoff to prevent overcooling. So this feedback model doesn't produce high entropy gas. It produces low entropy gas with fairly high pressures that it then preserves by artificially disabling numerical cooling, or radiative cooling. So these galaxies span more or less the range of mass that we think the Milky Way might live in, and they're of fairly moderate resolution, better than you would get from a cosmological box like Eagle or Illustris, but not quite at the sort of cutting edge that something like Latte is doing. And you can see from looking at the H1 column density maps of these things that they have a variety of merger histories. Some of them are in the process of merging at redshift 0. Some have been shredded by a recent merger, but also all of them have very large H1 column densities above the disk. This is a bit of evidence that our feedback is working. But to actually know what our feedback model is doing, we first decided we would compare to the previous cooling shutoff blast wave model, no feedback, our new Superbubble model, and a model of the Superbubble feedback with twice the supernova energy in order to sort of mimic these early feedback models that add additional forms of energy. And so we simulated the same initial conditions 4 times, and what we found was that with this Superbubble model, we actually get the correct stellar mass to halo mass relation, matching the sort of abundance matched observations for the entire evolution of this galaxy. And we get a flat rotation curve with a tiny bulge to total ratio. About 9% of the stars in this galaxy are in the bulge. With the blast wave cooling shutoff model, because you can't drive out buoyant gas and it just kind of sits there, you end up building a massive bulge. About half the stars in this blast wave galaxy lie within the bulge. So why is this? What's happening that's different here? We're putting in the same amount of energy, so why are the results so radically different? Well, if we look at the star formation rates, of course, we get more stars, so we see more star formation rate in the blast wave case. But if we look at the outflow rate, and most importantly, the mass loading, the ratio of these two things to each other, we can see that with the Superbubble model, we kick out more mass for the same amount of stars formed than the blast wave model by about a factor of 10. And so we get mass loadings of around 10 up until about redshift 1.5. After that point, things ramp down and you end up having mass loading falling around order unit. And this is really important. It's important both that we're getting high mass loadings at high redshift, but also that we're getting low mass loadings at low redshift. Because these high redshift outflows are what are required to prevent bulge formation, but not having highly mass loaded outflows at low redshift is important to preserving your disk.
So if you look at the low angular momentum gas that would form your bulge, we get much higher outflow rates of this gas when using the Superbubble model. But the disk-forming gas, the stuff that accretes at low redshift, is kicked out basically no better than before. Yep? We're measuring this outflow rate across a fairly wide annulus between 1/10 of the virial radius out to the virial radius. So this isn't the kind of very close-in outflow rates that you would measure from like a stratified box simulation. It's very comparable to the mass outflow rates that the FIRE group has measured in Muratov et al. 2016. This is just mass. I don't do any cuts in terms of temperature, density, etc. So once we felt like we had got a bit of a handle on how this feedback model was actually working, what it was doing differently in our galaxies, we then turned to answering, or at least trying to answer, this big question that's been talked about a little bit already in this week's talks. The big question is, why is there a turnover in the galaxy luminosity function and in the stellar mass to halo mass relation at about 10 to the 12 solar masses? So both, why is there a turnover, and why here? So the standard picture, the hand-wavy explanation that most theorists will throw at you, is that stellar feedback is very important and gets less and less effective as you go to high masses up until this L star point. And that AGN feedback is more and more efficient as you get more massive than this L star point. And so since we have this new model for supernova feedback that we felt was very physically motivated and seemed to be doing the right thing, we thought, well, why not just see if supernova feedback gets less and less efficient as you approach this point? So if supernova can do it all, then you should see that this turnover occurs even if you don't include AGN feedback. And as Betteridge's law of headline says, any headline that starts with a question can be answered with no. No, supernova cannot do it all. And in fact, as you approach this particular mass of 10 to the 12 solar masses, you rapidly transition from having galaxies that form the correct amount of stars to galaxies that are forming 2 to 3 times too many stars. And very interestingly, not only are you forming too many stars, in every single case where you form more stars than you would expect from the observed stellar mass to halo mass relation, you also form a very dense, massive bulge with rotation speeds as high as 700 kilometers per second. All this comes down to, as we found, due to the fact that mass loading has a universal scaling. So whether or not you're looking at the galaxies that form the correct amount or too many stars, you get roughly the same mass loading scaling as a function of either your disk mass or your virial mass. And you also find that you transition between kicking out a mixture of cold and hot gas in low mass systems to only being able to eject the hottest outflows. And interestingly, if you look at how this relates to the disk escape velocity, you find that your mass loadings plummet right around when your sound speed approaches the escape velocity of this disk. And this is really interesting as well, because a similar study has found the same thing happens when you approach the escape velocity of your bulge when fueling an AGN in a simulation by Johann Dubois from 2015. It also matches quite nicely with right around where an observational study by Kaufman et al. Found powerful AGN tend to occur. But this can't be the only picture. We know that there's a lot more going on than just a disk. So how ultimately does gas move through the CGM? So we know that gas has to get out of the ISM in order to drive an outflow. But then it has a much, much longer way to go as it flows up through the CGM. And ultimately, what's driving this gas? Is it kicked out ballistically by an energy-conserving process or a momentum-conserving process? Or is something else driving it? Something exotic like cosmic rays or magnetic buoyancy? And how does it ultimately interact with the material that's being accreted? Well, we have to now kind of go back and think about what governs the flow of gas within the CGM. So we know that energy and momentum is being injected by feedback. We know that gravity is pulling things in. We know that hydrodynamic drag may be important. If the cloud is close to our cooling, the peak of our cooling curve, we know that it might be losing energy as it rises. But also, we know that buoyancy can actually push the cloud up or down. So really, we can wrap almost all of these processes into buoyancy. All of these processes are related ultimately to the mass and the entropy of this cloud. Cooling removes entropy from the cloud, feedback gives entropy to the cloud. And the cloud will be neutrally buoyant when it reaches a point in the corona, or the CGM, where it has the same entropy as its surroundings. So just to give a bit of a review of what Mark already told us about yesterday, we can quantify the entropy using this sort of pseudo-entropy value that's commonly used in the cluster and X-ray community. It's directly related to the real thermodynamic entropy. And whether or not a portion of gas, a blob, is buoyant neutral, or is going to rise buoyantly or fall buoyantly, comes down to the Schwarzchild criteria. If you have more entropy than your neighborhood, you will want to rise. If you have less entropy than your neighborhood, you will want to fall. And if you're bobbling around that area, you'll bobble with this Buoyancy frequency that's related to the gradient of the gravitational potential and the gradient of the entropy. So to test this idea that buoyancy may actually be an important driving force for outflows, the obvious thing to do is to look at the entropy. So if we look at the entropy of gas in units of the virial entropy of our halos versus its radial velocity, you might think that buoyancy actually is not the thing to look at. In fact, it looks like most of our gas is inflowing except for a tiny little peak of gas right just below our virial entropy. But remember, it's not the total entropy that determines whether you're buoyant. It's your entropy gradient, whether or not you are have more entropy than your neighborhood. So if you look at the entropy gradient, that is the difference in a gas particle's entropy versus the average entropy at the radius it's at, there's a keen difference here between negatively buoyant and positively buoyant gas particles. In other words, we see an outflow of positively buoyant material and an inflow of negatively buoyant material. Also interesting to note here is that these particles are not moving very fast. In our simulations, we don't typically see 1,000 km per second outflows. And in fact, if we watch as things move through the entropy radius plane over time in one of our Milky Way-like galaxies, we actually see a pretty simple picture here. Stuff cools down here along this power law entropy profile. This is sort of the bulk of the CGM. And as you can see, stuff's losing entropy, joining the ISM. And then feedback gives it entropy, kicks it up to this high entropy plane here, where it rises, because this stuff is embedded in this stuff. You end up getting this cycle, this fountain, that gas can live along this high entropy slope, slowly bobbling its way upward until it finally loses entropy from cooling, falls down, and reaccretes. And because this reaccretion cycle takes place over a long time period, it can actually keep a significant amount of mass out of your ISM. So we might want to try and derive a set of equations to understand this. So we know from these classic studies, Lever, McClough, and McCrae, although Martin mentioned that we might not want to trust them too much, that we can calculate a density and a temperature as well as a radius for our superbubbles. Well, if we invert our radius here to find time as a function of the bubble radius, we can then plug this into our density and our temperature to find the superbubble's density and temperature as a function of radius. And if we assume that the superbubble then breaks out when the radius reaches the scale height, we can calculate an entropy for the superbubble's heated gas, not the stuff in the shell, but the hot bubble inside, as well as the entropy of our halo itself. And note that these are on the same rough order of magnitude, which means that this superbubble heated gas may not be able to make it all the way out to the virial radius, but if our if our entropy follows a power law relation, it may be able to get very close to the virial radius and spend a long time there. So Mark derived an equation of motion for buoyant gas in a 2017 paper that, if you include the effects of drag as well, you can plug in these previous relations and actually look at how different kinds of superbubbles embedded in its galaxies can drive entropy-driven outflows, totally different in their behavior from ballistically driven outflows. And in this movie, you can see for a Milky Way-like disk embedded in a growing halo that different sized star clusters become less and less effective at driving outflows. In fact, pretty quickly, they're not even able to get up to the virial radius as you grow in mass. And let me just repeat that movie once, because there's something really important here. Even our most massive star cluster, around 10 to the 5 solar masses, once you exceed a halo mass of about just over 10 to the 12 solar masses, you no longer are able to drive buoyantly outflows up to the virial radius. So not only does the amplitude of these perturbations drop, the Brundt-Weissala time, the frequency of them, decreases as well. So that means two things. One, you're not going to be able to kick things up as high where they will have shorter or where they'll have longer cooling times. So they'll reaccrete, rejoin the ISM, form more stars. And they won't spend as much time up there. So it will rapidly reaccrete material that you've been able to kick out buoyantly. This actually points very strongly towards why it is that 10 to the 12 solar masses is such an important scale for galaxy formation. It's the point at which winds and outflows that are driven by buoyant superbubble heated gas are no longer buoyant enough to actually leave the ISM for a significant amount of time. So I'll leave my conclusions up here so we have a few minutes for questions. Thank you very much.
So have you included magnetic fields, because this kind of bubbles, they're used in solar physics a lot, and they're always, magnetic field is always included.
So no, the simulation code I used in my PhD doesn't include MHD, but we did do a few tests because it's known that magnetic fields reduce thermal conduction. So across field lines, you can't move the electrons that do thermal conduction. But the important thing is that because thermal conduction is such a strong power law of your temperature, if you decrease the conduction coefficient, your bubble gets hotter, and that acts to increase the mass flux, canceling out much of the effect you get from a reduced thermal conduction coefficient. So you can see here, you can actually reduce the Spitzer conduction coefficient by a factor of 100, and it only changes the amount of mass that you entrain in this hot bubble by about a factor of 2.
So, excellent talk. So all this depends on the entropy gradient of the background atmosphere and the entropy of the rising bubbles.
Yeah.
So the important thing is what one assumes for the background entropy. In clusters we know it very well, we directly see the
Of course. So I'm lucky enough to be a simulator, which means that any kind of number I want, I can pull out of one of my simulations. So I do find that once the sort of really turbulent high redshift stuff has settled down, you do get a pretty constant power loss slope in your entropy gradient. But the derivations I've done in the paper that should be out by the end of the month, all it assumes is that you have a power law entropy gradient with some slope. So you can do the derivations assuming any slope, and of course that will change the answers you get, but it's a general process.
two questions. First is very, very simple and usual what I ask you. What is the numerical resolution in your cosmological simulations?
So we're using a Lagrangian code. So our mass resolution for our particles is about 2 by 10 to the 5, and our gravitational softening resolution is 300 parsecs. So we're not resolving detailed structures of the ISM. That is, I hope, captured by the subgrid model that I included.
Okay, another question, also simple. Don't you think that the numerical diffusion and numerical conductivity can be much higher than your physical conductivity?
That's actually a very interesting point. One of the major problems with SPH as a Lagrangian method is that it's purely Lagrangian, which means that it actually is numerical conductivity and diffusion is completely absent. So you have artificially suppressed mixing unless you include explicit mixing terms. So it's possible that numerical diffusion is moving heat around because we do include an explicit turbulent diffusion approximation. But we don't have the same kind of issues you have with Eulerian.
What is mass resolution in this case?
Sorry?
Mass resolution in this case? For numerical conductivity, or numerical thermal conductivity.
We don't include numerical, like we don't have an artificial conductivity term.
Let's go to the next question.
Okay, so I'm really interested in this entropy fountain, and so I have just two questions related to it, and one is just to check if I'm right. So, in the entropy fountain, does that mean that earlier on in a galaxy's history, the time scales are longer for material in the fountain?
Absolutely.
Okay, and so then when you compare this to like a traditional kind of like Bregman ballistic fountain, are those time scales should be constant, right? Like those don't evolve, and then how do the time scales compare between the entropy fountain?
So I haven't worked out the full set of numbers. I was really hoping to have this paper done before this conference, but I was slower than I hoped.
What's your instinct?
But my instinct is that the time scales at high for like a Milky Way type object at redshift 0, what was going on at redshift 2? You could have stuff cycling through this fountain that would spend a giga-year plus in that fountain process. So you can have stuff. You could have stuff that you take out at redshift 2 that doesn't come back till redshift 1.
What metallicity do you put into the simulations?
So you start with 0, and metals are enriched self-consistently. So all of the metallicity is whatever metallicity has been generated by the stars that are formed in the cosmological box. So at high redshift, all of this stuff is going to be a fairly low metallicity, but by redshift 0, most of our galaxies have around solar metallicity for their ISMs.
Okay, and does that apply to the CGM, which is the surrounding stuff that it's expanding to?
A huge chunk of the metals, like more than half of the metals are out in the CGM.
Okay, so it's all built up in the model.
Yeah.
Okay.
So, I try to stop within your talk as an ovation.
Thank you. Thank you.
Because I've seen things in your movies that I've only seen in my head before. Can you please show your entropy evolution movie again?
This one?
The one.
This one. So yeah, this is from the simulations.
Right.
Yeah.
And so what I was watching was your ridge line for the cool entropy branch.
Yeah.
It sure looks like it's like an entropy to the, it looks like R to the 2/3 power.
Yeah. So I think what I put in here is 1/2 power, but 2/3 fits pretty well too.
Right. 2/3. Because it's the other one, and I'd be dying to know what the equivalent kind of free fall time ratio is.
Oh, yes, I can calculate that. I'll calculate that and send you an email.
Please. And third thing, in this most recent paper trying to understand the Limits of 10, I found that turbulence probably affects the critical ratio. And I'd be interested in knowing, again, whether the inner parts are more turbulent than the outer parts.
Yeah, that's. Well, would be interested too.
Okay.
Excellent,
All
thank
right,
you.
let's move on. Let's give him another round of applause.